Good morning, it's the physics video lecture once again. Physics 105A, video lecture 32. And we finished up last time with an explanation of how Newton found his law of gravity. So I'll start with that again. We're working through the central force problem. And just to review, we had Newton gravity derived by analyzing the orbits of a planet around the sun and inserting Kepler's third law at a crucial spot. So what we're left with is this idea. The force is a central force. It's proportional to the product of two masses divided by the separation distance squared. So that's the inverse square law. Newton generalized for two arbitrary point masses. Right? The sun and the earth are by no means point masses, but here M1 and M2 distance separate MR, so we say it's a central force and it's an attractive central force. So this here is the magnitude, and I'll just write attractive central force. And finite masses are treated this way. So suppose I have M1 and M2. As long as they're spherically symmetric, then we can take that R separation distance from center to center. We'll prove next semester a number of things about this, including that statement. We're just going to take it as given right now. Because one interesting case in gravity is, say, a mass of the Earth, or the Earth with its mass m and radius r, and some small body standing up there near the surface, okay? Then we're actually attracted, according to this law right here, to this point at the center of the Earth. Okay, so that's just for some context. We're going to simplify things and just talk about the central force problem again and work our way through the Kepler problem. So our idea is to derive all three of the Kepler's laws that we found last time, just for the general case of two point masses. Okay, so much for review. So next, back to the central force problem. Right? We've reduced the two-body problem to a one-body problem, and that's what it's going to look like now. Okay. So what did we have? We have f of r divided by r. This, of course, is the very celebrated example, but we'll have other examples. So yeah, I'm going to go ahead and review that. We know that it's a central force. We have a potential energy of this form. It's an R. We have conservation of energy. And motion's restricted to a plane, and we had, well, let me send this up here. I'll just continue our facts right under here. So yeah, so what else did we have? We had angular momentum, R cross M R dot, and it turns out that was constant that allowed us to discuss motion in the plane and bring in the plane polar coordinates so that motion in the plane, so that we have plane polar coordinates, and having those we found, then our vector R, or R hat, R dot with R dot, R hat plus R phi dot, phi hat, and our magnitude L was M R squared phi dot. So what we have to do now is continue along these lines here. We're going to treat our whole central force problem in plane polar coordinates, and we have to, take the forces and obtain the potential energies. So that's our next task. And in fact, I'll treat these interchangeably. That is to say, we can discuss knowing the force or knowing the potential energy, right? The potential energy for this is just going to be -1/r, and we'll get to that in a while, but right now we'll just treat the potential energy as a given and continue on with this. So here's what we have. We've already got the plane polar coordinates, but we have to express the energy in terms of plane polar coordinates. So that's our next topic here. Next, energy in plane polar coordinates. And that energy expression is this one. So we have 1/2 m now the r dot squared is this expression here squared. So let's go ahead and write r dot r hat plus r phi dot phi hat dotted into itself So that's the r dot squared, mr dot squared, plus u of r is equal to E. And now we just expand this out, but there's nothing to it, because r hat squared is just 1. Remember, these are unit vectors that are orthogonal, and r hat dotted into phi hat is 0. So cross terms go away, and we have simply 1/2 m r dot squared plus 1/2 m r squared phi dot squared plus u of r is equal to E. So there's our energy. And I'm going to bring the angular momentum in here, equals mr squared phi dot. Okay. So you can say this is the set of differential equations that we have to solve. There are two unknown functions, r and phi. Okay. And there are two equations. One's here in boxes. And these are first order equations because we already took care of, we got our energy conservation. So we have two first order equations. They're coupled because this one includes r dot and phi dot, r and phi dot. So they're coupled first order differential equations, and we now have to solve this, and we're going to solve it. And I should point out, and we have these constants here. The energy and the angular momentum are conserved quantities in the motion here. Mass is a parameter. we have two coupled first order differential equations, or we want to find R of t, phi of t, and in fact what we're going to look for is R as a function of phi later on. But so how do we solve these? These are our problem, and of course what we're really after is the, Newton's law version here, but we want to do the general discussion in which we still just have some potential energy. Okay. So what happens next is that I replace phi dot in this equation with phi dot from down here. Okay. Just going to solve for phi dot, plug it in here, and square it. And you can see what happens. We're going to have, solve for phi dot, insert in energy equation, and what do we get? We get 1/2 mR dot squared. Now this thing here, phi dot, when we square, we're going to get L squared, and R to the fourth going to cancel the R squared, so we end up with plus L squared over 2mR squared plus U of R is equal to E. And what we've achieved here is really important. We have a differential equation, first order in R, and you'll notice phi is not in there anymore. So this is a first order differential equation, and we've spent, and it's in one dimension, 1 degree of freedom. We've spent a lot of time figuring out how to solve this, and that's all going to be applied now. So what we do here, because with just R, R and R dots, we draw parentheses around this thing. This came from the kinetic energy, right? This term came from here, but we're going to lump it in with the potential energy and refer to this here as the effective potential. U effective of R. Effective potential. And the first time people see this, they're sometimes a little confused by it. But what we've done here is just turned this into a formal 1 degree of freedom problem of the type that we solved earlier. And I'm just going to write it about some different color. So here's what I'm going to write. Recall 1/2 mx dot squared plus u of x equals E. Right? When we were talking about forces in one dimension that were a function of the position, we ended up with the conserved energy in this thing here. And this that we've studied in the numerous cases is to be identified with this up here. So because this is just a function of R, we lump it in with the actual potential energy, and we have an equivalent situation here. Only thing we would say is different in our central force problem is that R is just restricted to positive values. Here with X, it could have been the whole real axis. So R is restricted to positive values, but other than that, we have a formal similarity to our 1 dimensional problem. And all of the things that we learned about solving this and analyzing it are going to come into play up here. Good. So yeah, this term effective potential, very important one. Formally, we've turned this into a one-dimensional problem. So let's study some of these effective potentials. So let's call this potential energy and the effective potential energy. I'll just call it effective potential. So let's do the example that we already know about is U of R is equal to 1/2 K R squared. And what would its graph be? In a, it's just the right-hand side here, right? Because we're restricted to R equals R positive. Of course, back here in our earlier work, so I'll just put a note, when we had U of X equals 1/2 KX squared, we had that potential energy and we had oscillations, okay? But right now we're doing the central force version. This is just here, not to confuse you, but just to remind you what our tactic was down here. What we want to do now is graph the effective potential. So the effective potential is going to be an addition of these two expressions. I'll do this right under here. Good. So yeah, this is what we're dealing with. So underneath here, U effective of R is equal to L squared divided by 2M R squared plus 1/2 KR squared. You may recognize things like this. We had them on our previous homeworks, maybe on the exam. But this time we're actually going to work with it. Here is this effective potential. I'll just outline a bit what these two individual functions are. This is the 1/R squared. We know it diverges here. It comes down like this. And the 1/2 KR squared comes up like that. So if you add those two functions, we have these 2 points, we're right there. And we have this on the one hand and this on the other. So this is a nice smooth curve with a local minimum asymptotic behavior. Very nice. So what is the meaning of this? In the context of a 1 degree of freedom problem, this is something that if it has a certain energy value here, say there's our energy, then clearly we're restricted to motion in this potential well. And in fact, here's a minimum, I'll call this R0. And if this were purely a one-dimensional problem, you'd say, good, the particle is just sitting there in the minimum of the potential well, supposing it has this energy here, which I'll call E0. Okay. But if it has more energy than E0, say just this E here, I could call it E1. Actually, it's supposed to be 1. If it has more energy, then it moved between you know, it's restricted, but it moves between 2 points. Let's get another color here in the mix. So for E1, we could have R minimum and R maximum. So these are just the kind of analyses that we did in the past with this situation here, However, then we have to remind ourselves that this is an orbital problem. So what's going on here at R0 is that the particle has a fixed R sub 0, but that represents a circular orbit, right? The radius of orbit is unchanging. We still have, you know, the angular momentum expression there. So yeah, as a two-step investigation, we can just investigate this equation here and the effective potential as a one-dimensional problem. Then we have to remind ourselves that we actually have an orbital problem. So talking about this here, let me make my third point. For E equals E0 with U effective of R0 equal to E0. That's just what I drew right here. We have L equals M R0 squared E dot. Remember, that was our expression for the angular momentum. And we could even say equals M R0 squared omega sub phi, because this phi dot, which I'm calling omega sub phi, is a constant. So I'll write with phi dot is constant, because L is constant, M is constant, we have a constant radius, so that, and so what we're talking about here is a circular orbit, i.e. a circular orbit. And now you can see what it means to have energy greater than E0. Now the motion in R is between R minimum and R maximum. Those are minimal radii and minimum radius and maximum radius of an orbit. That could be an ellipse. Doesn't have to be an ellipse, but it could be. Because now the radius is changing at the same time that the angle is being swept out. I'm going to consult the clock here. Okay, fantastic. So that's what we have here. So this analysis is really important. I'll even write down that next part. You're working to the left. 2, 3. Number that's 4. If E equals E1, right? I'm still talking about this graph here. Then R min less than or equal to R less than or equal to R max. Okay. So that being the case, R is no longer constant, and we have this phi dot is equal to, I'm just going off of this expression right here. Okay, solve for phi dot, which is the rate of change of the angle, is L, which is a constant, over M R squared. Okay. The R naught was because it was a constant, but now it's just a general R squared. And you can see when R is smaller, phi dot is greater. When R is larger, phi dot is smaller. Okay. So it's going to be a small picture, but you guys should expand on this picture here. I'm just going to squeeze it in the corner. So we've got two circles of radius, R min and R max, right? R min and R max. The motion is restricted to those radii, and yet angle's being swept out, so we're looking at some kind of orbit. And it doesn't have to be a closed orbit either. Okay, but it's being swept out. It's always restricted between R min and R max. This is worth being a much bigger sketch, so make a big one in your notes. Okay. But the thought process, working from right to left, should be clear. Okay. So yeah, by turning this, by just interpreting this as part of a potential energy, we just have an analysis of a one-dimensional problem. Then we come back and combine it with the angular momentum expressions. Okay, so having done this, we are going to look at the actual Newton potential. Actually, I take that back. Having done this example, we will look at the further solution of this expression here, or the further analysis. I actually want to do an analysis of this that'll give us some insight into that picture some more. Okay, good. Let us erase this. I'll erase this, I'll probably rewrite it. Let's see what we have here. Nope, changed my mind again. We're going to do the Newton potential. So, because we'll really just get a good discussion of this. We'll continue with this type of discussion, but now Newton potential. So for Newton gravity, we write F equals F of R, and that's just R hat. Remember, the R divided by magnitude is the unit vector R hat that we also use. Okay. So we have that with F of R. We're just going to say it's minus alpha over R squared. Now we need the minus sign because R hat points away and we have an attractive force, okay? Alpha is just simpler than writing mmg, and it's more general because there are other central forces of this type, like the Coulomb force, for instance. Okay. So that's what we have, and U of R minus integral negative alpha over R prime dr prime to R. So we've got the integral of alpha over R prime, that's going to be, squared. R prime squared. So get rid of the two minus signs, and then the integral will be minus alpha over R. That's our potential energy evaluated from A to R. And what we do is, and this is the convention, minus alpha over R plus alpha over A, but this goes to 0 as we send A out to infinity. So the convention is that the potential energy vanishes out at infinity. So that limit U of R as R goes to infinity is equal to 0. That's the standard convention with the gravitational force. Its potential energy, we choose the constant, so the potential energy out at infinity goes to 0. And of course that allows us to graph, I'll do it right here, U of R like this. It's got the minus sign in front of it, right? Showcase it here, minus alpha over R. And because it's negative, it has this generic form like that. Vanishes out to infinity. Out at infinity. Good, that's our potential energy function. And now we're going to construct, and you're going to recognize it as something we've done in class. Maybe, did we have that on the exam too? Something similar. Okay. We're going to construct the effective potential now for this potential energy. And really repeat this entire analysis, except there's another really interesting point that comes into the mix. So we'll repeat this analysis for the Newton potential. Let me consult the clock again. Yeah, we got this. Great. Okay, so we'll start on the left side this time. So we'll write everything down. We have a half m r dot squared plus L squared over 2mr squared plus u of r is equal to E. We now know that's the effective potential. So now U of R is R minus alpha over R, and U effective of R is L squared 2mr squared minus alpha over R. So this is the really interesting and rich case that we're studying. Let's draw a nice sized graph. This one, we want to have some room here. We need some room above and beneath the axis. Because when we construct this one this time, we have the L squared over 2mr squared coming down like this. But we have the minus alpha over R that's coming up like I had above there. And if you just look at them, you don't know which one dominates. If you look closer, you see that for small r, the 1 over r squared dominates the 1 over r. Okay. So for small r, is going to be up here. And for large r, this one gets, vanishes much faster. So for large r, this one dominates. And that means we're definitely going under the axis. Let's see if we use a blue on this one. So the generic form of this is going to be something like this. And I want to draw it nice and exaggerated so that we can analyze this situation here. See, I'll make this one come out to infinity a little. There we go. So that's the idea. That's our effective potential of this type, the Newton potential. And now we can repeat what we had last time. We can clearly see there is an R0 corresponding to an E0, and that corresponds to circular orbits. Okay. So U effective R0 equal to E0 circular orbit. Of course, on this graph, it's just sitting there, but we know combined with this angular momentum, we've got a circular orbit. Now let's do an E sub 1. we've got an E sub 1, and we'll come out to here. We'll have an R minimum, and out here we'll have an R maximum. Very clearly not symmetrical, okay? So yeah, there's an R max, and there's an R min. So yeah, this is one case. So our second case, we have, as before, for E1, R min less than or equal to R less than or equal to R max. Okay. And we say those are bounded orbits. No longer circles. Well, we're of course going to prove that for this particular function they're actually ellipses. That's part of our discussion, Kepler's laws. But right now we just know that they're bounded. And my third case, this one's interesting as well. Suppose we have E2. So we have a positive energy as opposed to a negative energy. Yeah, actually we could say for these parts 1 and 2, bounded orbits have negative energies. Okay? We have a positive energy, so E2 greater than 0. You have an unbounded orbit. And we could say, okay, a particle comes in from infinity, comes into this closest point of approach corresponding to that energy, and then returns back out to infinity. Because there's angular motion in the same time, it turns out that those are hyperbolic orbits, hyperbolas, in the generalized Kepler problem. So that's what we have. These two are bounded orbits, both of these. So bounded orbits have this to your notes. When E is less than 0, and when E is greater than 0, unbounded orbits there. When E is greater than 0. So clock. That's going to be a good point to take a break. What I'll do is I'll make a homework problem to go along with this. So homework, consider central force is equal to a constant. So we have a constant central force. Now formally, it has to be an attractive force. So we have F equals minus F0. We don't have to have a 0 there. Let's just say minus C times R over R like that. Okay, where C is a positive constant. So what we're going to do for the homework is just construct the potential and the effective potential. So find U of R, U effective of R, that's an F, U effective of R, graph them so graph them both and locate the circular orbit. Locate circular orbit. What we're going to do next time we do this, it's just more of this discussion, a little bit different. And next time we're actually going to go into the Kepler problem proper, right? And possibly get to Kepler's first law, but it's coming up soon. Okay, good. We'll see you then.